We're going to continue our understanding of simple harmonic motion from what we did Monday. Remember, we did some definitions and basic explanation of terms for simple harmonic motion. We then did an analysis of the motion of a mass oscillating up and down on a spring. We analyzed the displacement, the velocity, the acceleration, also potential energy and kinetic energy of that mass in different positions along here. And we also used Hooke's law, force equals kx. At this position, the spring has no force applied to it, and as we stretch it, the force gets greater and greater and greater until we get to some value or some maximum distance. We want to stretch that spring, and we have some maximum force there. We're going to use this graph to derive an equation later on, so that's a significant graph. And then we made sure we understand what Hooke's law equation represented. So we identified all these equations that followed Hooke's law. And let's see if we can do an example problem involving Hooke's law. This is a kind of a basic one. When a family of 4 with a total mass of 200 kilograms steps into their 1,200 kilogram car, the car spring compresses 3 centimeters. So let's identify, we'll do part A first, identify information given. We know that the mass of the people stepping in the car is 200 kilograms. The mass of the car itself is 1,200 kilograms. Now the thing to remember here is that these springs which will hold the car up, they're the shock absorbers of the car. The mass of the car or the weight of the car is already pressing on those springs, and before the family steps in, the car is in equilibrium. Even though the springs are compressed, the car is in equilibrium. This mass right here causes the spring to stretch 3 centimeters. This mass doesn't cause the spring to stretch 3 centimeters. This mass does. And so the displacement from equilibrium is 3.0 centimeters. Convert that to meters, 0.030 meters. And in part A, what is the spring constant? So we want to determine K. This is the spring constant equation that has spring constant in it. This Hooke's law, F equals Kx. I'm leaving off the negative sign there, so we just need to understand that this force is a restoring force. It's always the opposite direction of motion, but the magnitude is the same. So we need to know the force that causes it to be displaced this distance. And we know the distance. We don't know the force, but we know that the weight of the people, or the mass of the people getting in the car, is 200 kilograms. So we can determine that force of gravity, which is the mass of the people times acceleration due to gravity. So we're going to take the force of gravity is 200 kilograms times 9.80 meters per second squared. We get that force of gravity to be 1,960 newtons. That is what we use in Hooke's law, because that is a force that causes the spring to stretch or to compress that distance. So now we have 1,960 newtons equals the spring constant K times the distance, 0.030 meters. And we get this spring constant to be 6.53 times 10 to the fourth newtons per meter. 6.53 times 10 to the fourth newtons per meter. That's the spring constant. Units for spring constants are newtons per meter. All right, now let's take a look at B. It doesn't matter how much force is applied to that spring. The spring constant, as the name implies, is constant. It doesn't change. So now it says how far does the car lower? So now we want to know the displacement from equilibrium position if it's loaded with 300 kilograms rather than 200 kilograms. So now the mass of the people stepping in the car are 300 kilograms. And we want to know that displacement. Again, we use Hooke's law, F equals Kx. But in order to know, we know K now. This K is constant, doesn't change no matter what the mass is. And we now want to know that distance. So we need to know this force. Again, the force is the mass, the new mass, 300 kilograms times 9.80 meters per second squared. We get that force of gravity to be 2,940 newtons. So now this force is 2,940 newtons. K is 6.53 times 10 to the fourth newtons per meter. We want to determine that X. And to determine that X, we should get 0.045 meters or 4.5 centimeters. And it makes sense that we put more mass in the car, more people, or more massive people, that it would go a further distance further than 3 centimeters. Now this is a common thing, type of information that problems give. They give information so you can figure the spring constant, and then they change the situation with the spring, so you have to determine something else. But the spring constant stays the same. So kind of remember that little scenario as we solve problems with simple harmonic motion, especially with springs. Let's expand our understanding of this spring system. Let's take a look at a spring, a horizontal spring, so we don't have to deal with the force of gravity and gravitational potential energy. To stretch or compress a spring, work must be done, which means we must apply a force through some distance to compress it or stretch it. Now, this is a spring that can be either stretched or compressed. You can kind of think as like a dart gun. A dart gun, you push a dart in, it compresses the spring, or a Nerf gun. A Nerf gun is a very common thing. In my days, it was dart gun. But Nerf gun, you take this Nerf ball or Nerf dart, and you press it into the Nerf gun, it compresses the spring, then you release it, and that spring releases that energy in the form of work done on that Nerf dart, or whatever you call that. So let's take a look and see what we have here. This is a spring. This right here is the equilibrium position, and it's been stretched some distance, x. That's its maximum displacement. If we let go of that, that spring is going to apply a force on that mass in this direction, a restoring force, causing that mass to move towards its equilibrium position. When you move it from here to x, you've done work on it. You've applied a force through some distance, so it has potential energy at this point. You release it, it's moving. At its equilibrium position, it's going to have some maximum velocity, or its maximum kinetic energy. It then goes past that and starts to be compressed. It'll compress, if everything is perfect, there's no friction, it'll compress through distance x. Its maximum displacement on the negative side. Now all the energy is potential. There's no kinetic energy because it slows down and stops. Then the force is in to the right, the opposite direction of the compression of the spring. And now the force moves it back to its equilibrium position. Then it just starts cycling back and forth like that. Let's take a look at this and see if we can derive some information here. So the elastic potential energy of a spring is given by the equation. We're going to derive that equation here just a little bit. I'm going to go ahead and give you that equation, then we'll derive it. The potential energy is equal to this equation, 1/2 kx squared. This is the spring constant, and that's the displacement from equilibrium position. Let's see how we got that. Well, it kind of starts with Hooke's law. This is a graph F on the y-axis, and displacement, or x. We'll put x, d or x there for the displacement. If the spring is at equilibrium, there's nothing on the spring, there's no force, but once we apply a force to it, the spring starts to stretch, and as it stretches, the force we have to apply to it gets larger and larger and larger until we stretch it to some maximum displacement, okay? This line right here represents Hooke's law, which is F equals kx, right? The further we stretch it, the greater the force. This right here is the maximum force that we stretch the spring to some distance, okay? Now, the force is not constant. We go from some zero to some maximum value. So if we want the average force that was used to stretch the spring from equilibrium to some maximum distance, the average force is simply going to be the sum of these two forces, 0 to some maximum value, 0 plus this maximum force divided by 2. That's the average. So this average force could be equal to 1/2 the maximum force. Now remember, work is equal to force times distance. We stretch this spring from its equilibrium position to some distance. We applied a force through some distance, but that force got larger as we moved it, so the average force was 1/2 the maximum value. So then this force that we applied wasn't the maximum force. This work is 1/2 the maximum force times distance that we moved it. Now this force right here is determined by Hooke's law. Fx, this maximum force is F equals kx. So instead of maximum force here, I'm just going to put kx. The x is this maximum displacement. So work is equal to 1/2 kx, and instead of d here, I'm going to put x. So notice what we now have. This work is equal to 1/2 kx squared. That work that we put into that spring is the potential energy. That's how that equation was derived. Okay? Now, since the object's speed changes, the total energy of the object is expressed by the equation. So at any point in time, this object has both potential and kinetic energy. At its maximum point, it only has potential energy because it's stopped and has no kinetic energy. At its equilibrium position, it has all kinetic energy, no potential energy. But anywhere in between, the sum of the potential and kinetic energy must equal the constant amount of energy that the substance has. So the total energy in the system at any point is equal to its kinetic energy, which is 1/2 mv squared plus whatever potential energy it has, 1/2 kx squared. This is the kinetic energy. If it's moving anywhere during this path, it has kinetic energy. And if it's anywhere other than its equilibrium position, it also has potential energy. Okay? So the total energy is the sum of the kinetic and potential energy. Note, x is the distance from equilibrium position. This is always from the equilibrium position. Let's take a look. The total energy must remain constant due to the law of conservation of energy, as long as there are no other outside forces. So at maximum displacement, where x equals a is the amplitude, which is the maximum displacement, v equals 0, the following equation expresses the total mechanical energy. Of that system. So then we're going to use this equation that we just have here, E equals, and then when we're at maximum displacement, where the displacement is the greatest value, the velocity is 0. And if the velocity is 0, we write this, 1/2 m times 0 squared is the velocity, that's the kinetic energy, plus 1/2 k, and x is the amplitude, the largest displacement. We'll put a instead of x there, 1/2 k a squared. This, of course, is 0. So then what we have, so the total mechanical energy of a simple harmonic oscillator is proportional to the amplitude. So that from this equation, E then, the total energy is equal to 1/2 Ka squared. This is the total energy of the system, 1/2 Ka squared. So at any point in this simple harmonic oscillator, something that's moving back and forth in simple harmonic motion, the total energy is equal to 1/2 Ka squared. Some of it may be kinetic, some of it may be potential, but all of it must be equal to this value right here, because the total amount of energy never changes as long as there are no other outside forces. Now we're going to derive some other equations. I already have this derivation done for you. You can pause the video and write the derivation. I'm just going to talk it through for just a little bit. So what if we want to know the maximum velocity of this simple harmonic oscillator? Remember, the maximum velocity is going to occur at the equilibrium position. That's when its maximum velocity, that's when its velocity is the greatest, at equilibrium position. And at the equilibrium position, the amplitude is 0. There's no displacement from the equilibrium position. So then if we want to derive an equation for the maximum velocity, we start with this. This is 1/2 K squared. This is the total energy of the system, which is equal to the sum of the kinetic energy and potential energy. For maximum velocity, the amplitude is 0 at the equilibrium position. So then what that means, this is the total energy, which is 1/2 K squared. The total energy must equal the sum of the kinetic and potential energy. But at equals 0, there's no potential energy. It's all kinetic energy. So the energy is equal to 1/2 mVA maximum squared. Remember, maximum potential energy is the same as the maximum kinetic energy, because this total kinetic energy, maximum kinetic energy, must equal the total energy of the energy of the system. So then, maximum potential energy is 1/2 Ka squared. That must equal the maximum kinetic energy, because all that potential energy converts to kinetic energy at the equilibrium position. So we set those equal to each other. We cancel out the 1/2. Becomes K squared equals mV max squared. I'm just going to switch this, move this quantity to the left side, this quantity to the right side. I just switch that equation there. I'm going to solve this equation for the maximum velocity. If I do that, I get that maximum velocity equals A times the square root of K over M. This is the equation for the maximum velocity at the equilibrium position. All right? It's a good equation, though. This is not on the information sheet, because you don't need this equation. You can actually use this equation to solve any of the problems that we're going to do. This is a nice equation that I'm going to do another equation also. So what is the velocity of an object in simple harmonic motion on a spring at any position? Because we know the velocity at the maximum position is 0. And we now have an equation for the maximum velocity at the equilibrium position, but it's also moving at some velocity anywhere in between those positions. Let's take a look. We still know that the total kinetic and total potential energy must add to be 1/2 Ka squared. I'm going to switch these around. I'm just going to take these two, move to the left side, and this move to the right side. I'm going to solve this equation for V. Notice the 1/2 all cancel out. This becomes v mv squared equals ka squared minus kx squared. And I then factor out the k, mv squared equals k times a squared minus x squared. And notice this maximum velocity here has the variables amplitude, the constant, and the mass in it. Well, here we have amplitude, mass, and k in this equation, so I'm going to kind of put all those together. What I'm going to do, I factor out the k here, and then I'm going to divide both sides of the equation by m. Here's k over m, which is in the maximum velocity equation. And then I here have this a, so I'm going to factor out this a in this equation, which is kind of interesting. I'm going to factor out this a squared. This becomes a squared k over m. If I divide all this by a squared over a squared is 1, minus x squared over a squared. So then, now I want to solve this equation for v, not just v squared, so I'm going to take the square root of both sides. This just becomes v, and the square root of a squared times k over m is a times the square root of k over m, times the square root of 1 minus x squared over a squared. This quantity right here is the same as the maximum velocity. Maximum velocity, look at that. So I'm going to put the velocity is equal to the maximum velocity times the square root of 1 minus x squared over a squared. So this depends on its position from its maximum displacement will determine its velocity. This is another good equation to know. All right, so let's see how this can be used. Let's look at this example problem. A spring stretches 0.15 meters when 0.3 kilogram mass is gently lowered on it. And so that means the spring is initially set up like this. This is the spring. And we have at equilibrium position. So at this position, we then put a mass on it. And it is lowered. That mass causes it to be stretched. Oops, stretched. So this displacement is x equals 0.150 meters. 0.150 if you can see that. The mass that we lower on that is 0.300 kilograms. The spring is then set up horizontally with the 0.30 kilogram mass resting on a frictionless table. So now we have this spring set up horizontally with this mass on it. And then this position right here, I'll say this position right here, x equals 0, that's the equilibrium position. The mass is pulled at the spring is stretched 0.10 meters. So we're going to stretch this spring. It's a little longer. I'm going to stretch this spring. So then that this distance is 0.100 meters. Okay? From the equilibrium point. So this is the equilibrium, it's stretched 0.10 meters and release. So once this is released, it's going to start oscillating back and forth like this. Okay? So let's take a look. A, determine the spring stiffness constant. Well, look, we have information here that will help us determine the spring stiffness constant. We want to determine the value of K. Remember, the equation that has K in it is F equals Kx. This is Hooke's law. Well, we know the displacement from equilibrium position is this. If we know the force is acting on it, but we configure the force because we know the mass that causes it is stretched that much. So then this force of gravity is equal to mg. Mass is 0.300 kilograms times 9.80 meters per second squared. We get that force of gravity to be 2.94 newtons. So now we can figure out this constant. This is 2.94 newtons equals a constant times x, which is 0.150 meters. We get the spring stiffness constant to be 19.6 newtons per meter. So this information, first information, gave us the quantities that we can use to determine the spring stiffness constant. Now we're going to take this spring, it has the same spring stiffness constant because it is constant. Move it horizontally, we're going to then stretch it 0.1 meters and let it oscillate back and forth. So now, part B. Part B. The amplitude of the horizontal oscillation, A, we want to determine its maximum displacement. Well, we know its maximum displacement. It's told us that this displaced 0.100 meters. This is the maximum displacement that it goes, so that's also equal to A. So the amplitude is 0.100 meters. Let's look at part C. The magnitude of the maximum velocity, Vmax. So part C, we want to determine the maximum velocity? Well, we have an equation for maximum velocity. The maximum velocity is equal to a times the square root of k over m. Let's just put this information in. We now know the amplitude, we know k, we know m. So this maximum velocity is equal to amplitude, 0.100 meters, times the square root of k, which is 19.6 newtons per meter, divided by the mass of 0.300 kilograms. And if we do that calculation, we should get that maximum velocity to be 0.808 meters per second. Let's keep going. Part D. Part D is, here look, the magnitude of the velocity when the mass is 0.050 meters from equilibrium. So now, that's about halfway. Right? We know it's not at equilibrium, it's not at the maximum amplitude, it's halfway. So then x, the displacement, is 0.050 meters. And we want to know the velocity at that displacement. Well, we have an equation. That velocity is equal to, actually it's plus or minus that, because we took, in order to derive this, I should bring this over here, derive this, we took the square root of this. We take the square root of the number, it's actually plus or minus that. And so this will be plus or minus the maximum velocity, which we just solved for up here, times the square root of 1 minus x squared over a squared. Put these values in, that velocity is equal to plus or minus. I'll explain why it's plus or minus here in just a little bit. Besides just the mathematical reason, this is going to be 0.808 meter per second times the square root of 1 minus x. X is 0.050 meters, don't forget to square that, divided by a, which is 0.100 meters all squared. If we do that calculation, we'll get that velocity to be plus or minus 0.700 meters per second. Now the reason it's plus or minus is because at this point right here, if I release it when the mass is here, it's going to be going this way. So when it's 0.500 meters, it'll be moving this way, but also it's going to come back. When it reaches 0.500 meters from the displacement again, it's going to be here. That's also true for this side. It can be either 0.050 meters on this side or 0.050 meters on this side. It can be moving either left or right, so it can be positive or negative at either position. All right, let's go to part E. Part E. E up here says the magnitude of the maximum acceleration, A max of the mass. So now we want the maximum acceleration. What is this maximum acceleration? Well, we know Newton's second law. Net force is equal to mass times acceleration. So if we do the force acting on this object, the net force acting on the object, because we know the mass, we can get this maximum acceleration. Well, in order to get the maximum acceleration, we need to know the maximum force on it. Remember Hooke's law. Okay, force equals Ka. The maximum force is when the amplitude is the greatest. Hooke's law is force equals, we have here F equals Kx. The maximum acceleration is when the force is the greatest. The force is the greatest when the amplitude is the greatest. The amplitude is the greatest at this point right here. While the displacement is the greatest at this point. The displacement is the greatest at its amplitude, maximum amplitude. So we can get this net force. Do the spring constant we've already determined to be 19.6 newtons per meter times the amplitude, its maximum displacement, which is 0.100 meters. We get that net force to be 1.96 newtons. We then put that into Newton's second law. 1.96 newtons equals the mass, which is 0.300 kilograms, times the acceleration. We get that acceleration to be 6.53 meters per second squared. All right, let's continue on. Let's do, let's go to F. The total energy of the mass. It'll be F up here. We want the total energy of the mass. Right. Remember, the energy of this system is the same no matter where you are. We can actually determine the total energy a couple different ways. We can determine the total energy by its maximum displacement. Equals 1/2 Ka squared. Because we know the amplitude, we know K. That's the total energy. E total equals 1/2. Constant is 19.6 newtons per meter. Maximum amplitude 0.100 meters all squared. We get that total energy to be 0.098 joules. We could also determine it total is equal to 1/2 mv max squared. And if we do that, that's going to be E total equals 1/2 the mass, 0.300 kilograms, times the maximum velocity, 0.808. I'm kind of squishing things together here, meters per second all squared. We should get that total energy also to be 0.098 joules. You can do this either way. And then let's go to G. The kinetic and potential energies at half the amplitude. So then G, we want the kinetic and potential energy at half the amplitude, and half the amplitude is x equals 0.050 meters. This point right here. All right, well, let's take a look. Well, if we know the amplitude, we can get its potential energy. Potential energy is 1/2 k x squared. And so this potential energy is going to be 1/2 times 19.6 newtons per meter times 0.050 meters squared. We get that potential energy to be 0.0245 joules. What about kinetic energy? Well, I can do this a couple different ways, but one, we know the total energy, right? The total energy is equal to the kinetic energy plus the potential energy. Well, the total energy is 0.098 joules. We're solving for the kinetic energy, and the potential energy is 0.0245 joules. Solve that for kinetic energy, we get 0.0735 joules for that kinetic energy. So we solve for a lot of different things. It's all based on basically the law of conservation of energy and Hooke's law that causes this simple harmonic motion. All right? We're done for today. Take a look at your homework assignment and have that done by 10 o'clock tonight.